Yes. Okay, you get 2 points for that question. All right, if you apply the Laplace transform to y double prime, so you can do the same rule as you do for y prime. So if that were a y prime in there, remember it would be s times the Laplace of y minus y of 0, right? But that's for the first derivative. So for the second derivative, this is going to be a y prime and this is a y prime. And then you apply it again for the y prime part. So this is going to be s times the Laplace of y prime is s times the Laplace of y minus y of 0 minus y prime of 0. And then we'll just distribute s squared times the Laplace of y minus s times y of 0 minus y prime of 0. Did I do it right? Yeah. All right, so that'll come in handy well as we go through today's lesson. Oh, hi. All right, so today we're going to talk about using the Laplace transform on second order equations, which is why for the quiz we just talked about how to take the Laplace of a second derivative. So second order forced equation looks generally like that. And some common forcing functions are sinusoidal. We already know how to take the Laplace transform of an exponential, so that one we know. But then we've got these other sinusoidal and sort of products of exponential and sinusoidal functions. So we would need to know the Laplace transforms of those in order to use the Laplace transform to solve this. So if you wanted to come up with the Laplace transform of the sine of omega t, right, or just sine t, whatever, the definition of the Laplace transform, remember, is the integral from 0 to infinity of whatever your function is times e to the negative st dt. You can do that using integration by parts. So product, use integration by parts, and I've left that for you as a homework question. Don't want to like take all the surprises away from you. So until you can spend a little time working out the integrals to derive those necessary Laplace transforms, I'm just going to give them to you. So page 626 in your text has a table of Laplace transforms, frequently encountered ones. So we will use this extensively today to look up Laplace transforms that we don't know, and inverse Laplace transforms. And then this is also rules of Laplace transforms. We've got how to take the Laplace of a derivative, the Laplace of a sum, the Laplace of a constant times a function, and then some more complicated rules down here. The Heaviside times a shifted function, and the product of an exponential and a function. Okay, so we're going to start with trying to find the inverse Laplace of 1 over s squared plus 2s plus 5. So if I had given you this question last week, the first thing you would try to do is factor that denominator so that you could use partial fractions. But what's true about that denominator in terms of factoring? You can't factor it. There are no two numbers that multiply to 5 and add to 2. Right? So it's not factorable. So instead, I'm going to do something called completing the square. I'm going to try to complete the square in that denominator so I can make it look like maybe I'm working on trying to find an inverse Laplace. So I could make it look maybe something like that denominator or that denominator or that denominator. Right? I'm going to try to make it look like one of these things in the table. So I'm going to complete the square. Okay, so s squared plus 2s plus something would be a perfect square. Right? And then I'd have to subtract that same thing so that I don't actually change the value of my quadratic. All right, what should I add here in this first blank pink line so that this would factor to something squared? 1, yeah. Yeah, because then that would factor to s plus 1 squared. That makes sense? Quick shortcut to find that number that you would add there, take half of the coefficient on s and then square it. So half of 2 is 1, square it, you get 1. And then so if I added 1 here, I have to also subtract 1 here. So these first 3 terms factor to s plus 1 squared, and then 5 minus 1 is plus 4. So actually what I'm trying to find is the Laplace transform, or the inverse Laplace transform of 1 over s plus 1 squared plus 4. And then I'll see if I can find something in the table that looks like that. 1 over s plus 1 squared plus 4. Yeah. So omega squared, if you were looking at this guy, yeah. A would be 1 and omega would be 2, but my numerator doesn't match, right? I need my numerator to be 1. So yeah, that doesn't give it to me either. This one's pretty close, but omega is 2. So maybe I could, I don't know. Shoot, I should have done this before class. All right, so fancy little algebra trick. I am going to, the one that this looked closest to was this one, right? Except that I needed the numerator to be a 2 to match the omega down here, right? Because I have a 4 in my problem, so I would need my numerator to be a 2. So that was the one it looks closest to. So I'm going to do a little manipulation here and make this the inverse Laplace transform of 1/2 times 2 over s plus 1 squared plus 4. You can pull this 1/2 right out of the Laplace because it's just a constant. Oops, 1/2. And then my formula says that the inverse Laplace of that thing is e to the at sine omega t. And in my case, a is what? -1, yeah, and omega is 2. A is -1 and omega is 2. So this is e to the negative t sine 2t. All right, so there's 2 fancy algebra tricks you can use there to try to make something you're given match something from the table of Laplace transforms. You often have to do some fancy stuff to make it, to be able to use the table. Yes, for the final exam, I'll give you the table. Okay, so we now have enough to solve forced second order initial value problems using Laplace transforms. Now, we already have techniques for solving this, right? Like you could just solve the homogeneous, then make a lucky guess, take the sum of the two to get the general. but we're just going to use Laplace transforms so that we have another way to do it. On the exam, I don't think I won't require you to use one method or the other. You can do whichever one you like. Okay, so if you're using Laplace transforms to solve a differential equation, you start by taking the Laplace of both sides. It doesn't really matter. It does in this textbook. Yeah. Because the formula in the table says minus a. So if I wrote s plus 1, that's actually s minus -1. So the a value is -1 because the minus sign is part of the formula. Okay, the Laplace transform of y double prime, we went over that in the quiz. So the Laplace transform of y double prime is s squared times the Laplace of y minus s times y of 0 minus y prime of 0. So that's just the Laplace of y prime, of y double prime. Then I have to do plus 4 times the Laplace of y equals the Laplace of 3 cosine t. So I need to look up the Laplace of cosine t in my table. So I've got a formula for cosine omega t. So omega I would just pick to be 1. Yeah. So the Laplace, so I'm just going to have a 3 here. And then the Laplace of cosine t is s over s squared plus omega squared, which in this case is 1. 1 squared is 1. All right, so now it's just the same process that we did before. We should gather all the Laplace of y's on one side, anything that's not a Laplace of y put on the other side, and I can plug in any initial values that I have, right? Y of 0 and y prime of 0 are both 0 in this case, which is going to make this look a little simpler because that term and that term both become 0. All right, so on the left, I have s squared times the Laplace of y plus 4 times the Laplace of y. Yes, I'm going to do that in the next step. Yep. Yep, so then I'm going to factor out a Laplace of y here. And you have s squared plus 4 equals 3s over s squared plus 1. To get Laplace of y by itself, you divide both sides by s squared plus 4. So the Laplace of y is 3s over s squared plus 1 times s squared plus 4. So I'm going to find the inverse Laplace of that guy, and I'll be done. Easy, yeah. So let's look at the table and see if there's anything that looks kind of like that. Not yet. Okay, so these look like the sum of squares, right? This is 1 and 4 are both perfect squares. So both of those are sums of squares. So let's look in the table and see if we have any sums of squares. So potentials could be like that. I've got an s squared plus an omega squared. There's only one of them. And then there's that. And then these guys are s squared plus omega squared squared. So I don't think those fit. So it looks like sine omega t and cosine omega t are sort of the closest, but they don't look exactly like that. if you made omega 4, yeah, but the problem is that I have a product of two sums of squares down there. So how could I break that apart so that I could maybe write two fractions? What are you suggesting?
I don't know.
Yeah. So the I was taking the Laplace transform of cosine t. Yeah. So I'm just going to go to the next page here, and I want to break that into two fractions, each one having a separate denominator. One will have an s squared plus 1, and one will have an s squared plus 4, because I have inverse Laplace transform formulas for things that look like that. So I'm going to use partial fractions. So I want to break this into two fractions. One of them is going to have an s squared plus 1 and as a denominator, and the other one's going to have s squared plus 4. And do you remember what the numerators have to look like with partial fractions when the factors are irreducible quadratics? Yeah? They have to be linear. So this numerator would have to be as plus b, and this one would have to be cs plus d. Yeah, so up until now, we haven't seen any like this. The only partial fractions we've done are when we have linear factors in the denominator, or maybe a repeated linear factor we did once. But this is when the factors are irreducible quadratics. So s squared plus 1 and s squared plus 4 are quadratics, and they can't be factored any further. So the numerators have to be linear. All right, so we multiply both sides of this equation by the common denominator, and you get 3s equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. And now we get a bunch of algebra to do. We got to solve for a, b, c, and d. All right, so I got a FOIL over here, and I'm going to have as cubed plus 4as plus bs squared plus 4b. And then I got to FOIL these guys, and I have cs cubed plus cs plus ds squared plus d. And that all equals 3s. So now I got to equate coefficients. So on the left side, do I have any s cubed terms? No. On the right side, I have some s cubed terms. So my coefficient on s cubed on the right has to be 0. All right, so I'm going to collect my s cubes. I have this one and this one, right? So my coefficient is a plus c, and it has to be 0 because there's no s cubed term on the left. All right, then we'll look at s squared terms. I have this one and this one. So bs squared plus ds squared, the coefficient on s squared, if you added those, would be b plus d. That would have to be what? 0, because there's no s squared term on the left. All right, so now I'm going to look at my s terms. I've got this one and this one. So when you add them together, the coefficient becomes 4a plus c. And what does that have to add to? 3, because the coefficient on s on the left is 3. And then I have just the one constant term d. Oh, no, I have 4b. 4b plus d has to be 0, because there's no constant term on the left. Okay. So if I look at the first and third equations, they have the same letters in them. So that's just two equations, two unknowns. I could do substitution. A equals negative c. Then come over here, replace a with a negative c. So that becomes negative 3c equals 3. So c is negative 1. And then you come over here, which means that a is 1. For b came from when I was foiling as plus b times s squared plus 4. 4 times b is the last. All right, so then I have the same thing with the second and fourth equations. They both only have b's and d's, so b is negative d. So 4b plus, oops, hang on. Replace my b with a negative d. So negative 4d plus d is negative 3d. So d has to be 0, which means that b also has to be 0. All right, so b and d are 0, a is 1, c is negative 1. So we can break this up. A is 1, b is 0, c is negative 1, d is 0. So I have s over s squared plus 1 and negative s over s squared plus 4. So I'm going to go back to what I was working on, right? Now I can write this as s over s squared plus 1 minus s over s squared plus 4. So that's what all the work on the next page allowed us to do. Now, look at your table of Laplace transforms. Do any of them perfectly match s over s squared plus 1? Which one? Yeah, s over s squared plus omega squared. This one. And omega would be 1, right? So my inverse Laplace is cosine of 1t, cosine t. So then y is going to be cosine t minus, and then what about s over s squared plus 4? Same one, right? Cosine of 2t this time, because omega is 2. Yep. All right, so that's all the techniques. You now know how to find inverse Laplace transforms using completing the square and how to solve second order equations. And you have a few to try on your own.